Bueno, buenas tardes.
Good afternoon. We're here to present a presentation that we made in June this year in a conference that received an award. And thanks to INCIBE's sponsorship, we can be here to present this study. This study was conducted by Pedro García Teodoro, Lucy Alvarez, who will make this presentation together with me and myself. Regarding the table of contents of this presentation, it can be divided into two parts. The study we conducted, which is point 2 or item 2, which is the technique that we've used in order to block ransomware in an equipment in order to be able to detect it before it does its job, its malicious job. And then I'm going to introduce ransomware problems associated, the detection techniques, and then I'll explain to you the technique that we've developed. And I'm basically going to explain to you what ransomware is about. Ransomware is a form of malware or malicious software. It's a family of malicious software, and when installed in an equipment, it basically extorts or blackmails. Economic blackmail. Ransom is asked so that the user can recover the control of the equipment. We've focused more on encryption malware, basically accessing the hard drive of the infected equipment, encrypting all the files. Once encrypted, they are erased, and then they ask for a ransom to the user of the device or the piece of the equipment in order for that user to be able to regain control. So the data are hijacked, the data of the affected machine, and that's why it can be considered a DOS attack, denial of service attack. And there are other kinds of extortions that menace or threat the user with publishing personal data or pictures. This is a drive-by-download distribution. We can download them through Word documents, through the macros mechanism of word processors. Some can be downloaded through PowerShell scripts, which is the order interpreter for current Windows system, also through Trojans. Another very commonly used technique is phishing through an email that has embedded an executable file with ransomware, or a link that redirects us to a web page in order to download malware. Here you have the typical image of ransomware. On one of the screens you can see, once the data has been encrypted, you can see the screen requesting a ransom. Usually this payment has to be done in bitcoins in order not to be able to track the payment. There are different types of blocking, and pretty easy to bypass. Basically, mechanism is found through the graphic interface, and for example, blocking the use of the computer, modifying the user interface, and in this case these are easier to bypass and they don't generate serious problems. The most commonly used and that are most harmful are the crypto lockers, i.e. those ransomwares that block the files of the hard drive, fully block them. Then they ask for a ransom to return the control, and that sometimes happens, others not, and we need to be prepared not to receive that even if we do pay the ransom. And we have another more minority types of ransomware. For example, MBR, those that modify the MBR to prevent the booting of the system, or those that allow us to recover the control of the system if we send an SMS or a text message. The image is a bit small, but I wanted to show you with this slide that which seems to be a metro map is the evolution of ransom families. As you can see, if you take a look at the 2015-2007 range, 2015-2017, sorry, the number of families has been on the increase, and the forecast is that this number will grow in the upcoming years. In the lower part, if you take a look at 2016-2017, you see that there is an exponential growth, and the forecast is that it will continue to grow exponentially. This is due to the economic profit obtained. The estimated cost for this year are $1 billion. $1 billion, and in many cases, ransomware requests small amounts of money, 200, 300 euros. But the profit is made when good ransomware, when doing malicious actions, can infect thousands and thousands of devices, as we saw some months ago with WannaCry. So the economic profit obtained by cyber criminals is pretty high. And as a result, all the families of ransomware have grown during the past times, and the provision is that the family will continue growing during the next years. Here you can see how ransomware or encryption ransomware operates. Basically, in the case of an attachment, a phishing attachment, it's an attachment that is executable and that infects the device or equipment. Once the equipment is infected, what the ransomware does is to generate a public and a private password that are sent to a command and control server, so that the cyber criminal has the private password to decipher the files. So all the files in the disk drive in the hard drive are encrypted. The original files are erased, and the user then loses control over his computer because he no longer has access to his data. Once that is done, there's a screen or a window that appears asking for a ransom to be paid. For an individual user, we can be talking about 200 euros. For a company, it can be $17,000, $20,000. And usually cyber criminals end up negotiating with the victim to decrease the amount or reach an agreement regarding the amount to be paid. And there are some families of ransomware for you to understand the complexity, that in order to facilitate payment to the victim, what they do is to open up a chat so that the victim can chat with the cyber criminal that tells him how he should pay, the process that he needs to follow to recover his control. From the protection point of view, here you have a graph of LMG security company, which is very illustrative. So we apply the 3R mechanism: recovery, response, and reduction of risk. 3 R's. From the point of view of recovery, as I was saying, the most commonly used technique that we need to have as a backup once we are possibly infected, what is recommended is to, of course, have a backup copy. Recent, updated backups. And of course, You also need to have a policy for the updating of backups, and backups shouldn't be accessible through the internet because current ransomwares can not only infect equipment but to infect the entire network. So if we have our backups in network disk, well, probably that this will be infected as well. From the point of view of the response to ransomware, there are different techniques available. We focused on technical techniques through mechanism of deception. And as my colleague Lucia will explain, basically it's a matter of putting a trap. And that trap simulates an infinite file. So what we do is block, i.e. to allow ransomware to access infinite files and to block it. So once it's blocked, you're able to interrupt its activities and you're able to respond to ransomware, to detect the process that is executing the encryption, to kill it, and to block it. But there are other types of responses, training, a team of first responders in case incidents or events occur, but we have no time now to go into the details. And then we have risk reduction, i.e. Taking necessary measures to prevent infection. There you have some examples. Well, of course, many companies are hiring on insurance, are getting insurance to protect themselves from ransomware and other attacks. And from a technical point of view, the more effective solutions are the filtering of emails and web traffic so as to detect these potential infections. Of course, also to have two-factor authentication in place, conduct phishing exercises in-house so that the users and the different workstations are able to identify phishing emails, those emails that can be potentially malicious. Of course, it's very important to maintain software to reduce the attack surface, and we need to have antiviruses duly installed. Of course, antivirus don't grant 100% protection, but the best known malware can be protected against with these antivirus. Ransomware exploit vulnerabilities, and many antivirus are not effective in combating ransomware. One of the techniques we implement, as I will explain, has to do with this precisely. And the idea is putting traps to ransomware. And ransomware or non-ransomware will fall into the traps, and we need to be able to place traps intelligently. And it's very important that we integrate security, that we test security regularly. And we always have the doubt on whether we need to pay that ransom or not. Of course, if you pay the extortion or the ransom, entails additional problems. As you can imagine, the cyber criminal collects or cashes in money, has profits, and part of his job is to reinvest in new ransomware. So if you want to interrupt or break this vicious cycle, we need to, of course, not pay. Of course, if you don't pay, you're not going to be returned the access or the control over your system. And last year, 1/3 of the infected users did pay the ransom requested. And we see that this occurred more frequently in companies as opposed to individuals. So in companies, what we see is that if equipment is infected, that translates into downtimes. We've seen how hospitals have been infected with ransomware, police stations as well. We're talking about big entities, institutions, and companies, and this kind of extortion translates into downtimes. And in many cases, well, in many studies have shown that managers and the management and companies have some money on this side in order to pay this ransom in case of ransomware. From the point of view of defense mechanisms, I like to say that there are different types of defense mechanisms. I like to set the context so that you can understand our proposal. Our proposal has to do with behavior analysis. When a process is executed, in our case in an operating system, a piece of equipment, we need to see the interaction with the environment, and depending on that interaction, we will have to distinguish whether it's malware or legal software. Interactions with files, with network connections, potential modifications of the operating system, and there you have different proposals. The tool that we've developed is a behavior analysis tool. So it's not just about general analyses. We also generate what we call honey files to trap ransomware, to block ransomware when it attempts to access our files. It's very simple and it's quite effective, and all processes that attempt to access the file are blocked. Then we have some proposals for key deposits, and basically what they do is analyze all the iteration of ransomware with the system and with cryptographic material. So it basically stores info or data regarding the calls and the parameters in order to obtain that recovery key. The idea is that we can detect the interaction of that ransomware with the files, know what keys have been generated, and try to deduct the recovery key. Then we have the cryptographic primitive detection technique that analyzes the binaries in order to understand the behavior of ransomware, to know what kind of encryption system is used and how. And last, what we've seen is that another of the techniques that are being used is an automated learning technique that basically extracts the features of benign programs. And all these techniques, of course, have some false positives and false negatives that can pose problems. The proposal that we've designed, and soon Computer and Security will publish our study. We're still awaiting the date, but it'll be published very soon. And our proposal says that there is no false positives nor false negatives because we're able to detect all processes that interact with the honey file we've put into place. From the point of view of detection, what are the problems associated to ransomware? For those techniques that use behavior analysis components, one of the main problems that we've seen is obfuscation, to alter the code of the data of ransomware so that they are equivalent, but the visuals would be different. And this is used for antivirus, and in general we've seen this applied both for ransomware and malware, and when this technique is used, the signature is no longer valid. Then we have this so-called white box cryptography. Basically, what we do is to variate techniques different to encryption, so we don't see the traditional encryption behavior. And we've also seen the ransomware of the things. We are now talking about the Internet of the Things, and just as we have the Internet of the Things, we have the ransomware of the things. Basically, we're going to detect ransomware in sensors, devices. So currently it's not a major problem, but it will probably be in the near future. And in this sense, I like to say that one of the problems that we're going to encounter will be the combination of ransomware and rootkey. A rootkey is a software that hides from the eyes of observers, among them systems or network administrators. They hide, so what we see is that probably soon we'll see ransomware that hides and that will go undetected or will be hard to detect. And recently we've identified the so-called social technical attacks. Some months ago there was a ransomware whereby extortion or blackmailing. In this case, they were telling us that they were going to infect other programs. And what we see is that there's a pyramidal effect, and users can infect other users, meaning that at the end of the day, some will have to pay. And we've also seen the exfiltration of data for extortions. They're not asking for ransom to unblock the equipment, but in order not to publish data or information on the equipment. So in this case, it's an attack against the confidentiality and privacy. As you can see, there is a wide range of techniques, and all these techniques are very profitable for cyber criminals. Okay, I've provided you with a general overview on the techniques or technologies and the problems associated to ransomware. At this point, I'd like to describe to you the technique we've developed for the early detection of known or unknown ransomware. And not only to detect it, but also to block it and interrupt it as fast as possible. And I'm going to now give the floor to Lucia, who's going to take over the presentation. As Jose Antonio has said, we focused on encrypted ransomware, more harmful ransomware. Once they infect our files, if we don't have the private keys, we won't be able to decrypt. So we need to be able to detect and block ransomware before that encryption takes place. So we designed an early detection of ransomware based on honey files. Honey files is the name we've wanted to give to our trap. We've called this tool our locker, which is like a pun between ransomware and locking. And here you can see the system architecture. Our traps or honey files are distributed across the entire system of files, strategically placed or positioned so that ransomware accesses those traps or honey files before files. And these traps are infinite files or loops, meaning that a loop is created and we have time to detect it, we have time to block it, we have time to report the intrusion, and we also have time to implement the necessary countermeasures. So we want our system to block the ransomware, not to affect the valuable files.
The user is reported and countermeasures are implemented. This is a conceptual model and can be exported to any platform. What are the system requirements? Is it be efficient and effective? Is it give results in relation to ransomware and it does not corrupt our files? Is it be low consumption so that Users do not have to devote many resources from the system or embedded systems in the Internet of Things. So not too much memory. It does not. It shouldn't need a special privilege. It should be transparent and simple. Simplicity makes it more attractive. As a conceptual test, we have developed this idea, the Unix based on Linux. Once we see that it works and that it can be extrapolated to other systems, we are now working on it. We still have to see how do we create those tricks. First, we thought about an infinite file, but it consumes too many resources. So we thought about simulating infinite files, simulating the ransomware library. We should get to know ransomware behaviors based on the signature, so it's not possible. We finally came to the idea of doing with a fixed channel. They are processes of reading, synchronized reading and writing processes. This could comply with all requirements. Why did we select FIFOs? They are files that exist in the system with a name and hierarchy. We can refer to them as normal files. It allowed to communicate non-related processes of writing and reading. They do not have to be related processes. It's persistent. Once the process is acting on the FIFO, it goes on working. And finally, the most important is synchronization of reading and writing processes. In this image, you can clearly see the functioning. We create a channel or a pathway where we start a writing process that is never eliminated. When a writing process or a reading process comes in, the ransomware, it will read what is inside this channel. Because it's infinite, it gets blocked. At that time, our process realizes that they are accessing it, and we can implement the countermeasures. This could be used to any ransomware because they all have in common that if they want to cipher us, they will have to open up the file, and when they open up the file, we can detect them. This is a simple chart about the system. To the right, we will have our tool that has two processes. To reboot the environment, once we have the application, the tool, we would install the honey file, and I will explain how they are distributed. And we create the processes on this channel, the writing process. Once a ransomware is read, the reading process we created unblocks itself. So we are not using too many resources. We just have to execute the order of executing the intrusion and eliminate it. So we kill the ransomware process. How do we deploy the honey files? As we said, we don't want them to use too many resources. We cannot distribute honey files all over the directory to guarantee that nothing will happen. So what we do is to create one single file with links. We're not using too much memory. and we're not using hard disk memory. Those links are strategically located so that the ransomware, when getting to the directory, this is the first file the ransomware might read. It has an attractive name. Some ransomware are based on file extension or file names. What are the benefits of our tool, the R-Locker? Ransomware becomes fully blocked. Countermeasures are launched automatically. The writing unblocks itself without the system monitoring. Countermeasures are implemented, then it does not consume resources and it does not affect the rest of files. If the users open a FIFO, the message would only be, a file cannot be opened. This is just an image to give you an idea of our prototype, where we see a process in a background and is simulating. We executed a ransomware in a virtual machine, and this was the message, the warning. And we decided whether to launch the process or not. The experiment was first devoted to the channel to see whether we could control the reading and writing processes. Then we use Bash ransomware as a concept trial based on open source. We developed this tool first in Linux, and we use the concept in a trial to check it worked, and then we moved to real test. I will show you now a brief video, and then we could see that it didn't affect the rest of the programs that were being executed. The most common test, because the WannaCry had such an impact this year, and in order to simulate it in our environment, we use Wine, that is just a Windows environment, and this is a brief video. So we downloaded the sample, WannaCry. This is the program. We created a folder that is hidden, but you can see it. The name is My Dear. We started the process and we left it on a background screen. Then we have the honey file, the real FIFO, and we created a symbolic link. We created some files in the directory to see whether they can cipher it or not. We execute Wine simulating a Windows environment, and we execute WannaCry. It takes some time. It has to download all the files, and the first directory is being ciphered because the honey file is not the first. First, there's a warning about all processes, and I get a notification we eliminated. And here we will see information about WannaCry that is accessing the FIFO. If we go to documents, we see that it didn't reach the documents directory because the WannaCry started by the desktop, although it's not always the case. And we see it didn't get any of the directory files. It was just on the desktop. And we see all the files that were downloaded. And if we kill the process, sort of say the process stops. I've let it some time so that you can see that it can no longer cipher the files this will be fully ciphered. And because it's trapped in the first file, in the link in the directory, it couldn't go on reaching the rest of the files. And we see that those documents or files have not been ciphered. Now, our results were the following. Yes, ransomware was blocked. We had enough time to kill the process. Storage resources needed were only 2K, because that's the FIFO files. Space system requirements are super small. The process is stopped. It's not using any of the PC's resources. Response time could be 500 to 800 milliseconds. It's fully transparent to the users, and the idea is very simple. Once we test it and we see it works, we said we're now going to test it in systems very much used by users, and we are doing tests for Android and Windows. Android is not an OS, it's a layer on top of it, so it does not have all possibilities as an open source as Linux. We had problems in creating the symbolic link. The FIFO file had to be at a certain directory. We can do it at the Android kernel, and if we program it, it might have to work. About the future, about deployment, and those are our current projects. We are continuing with the project. We need to guarantee a coherent deployment of the system, but maybe the users might make a mistake, and we should take all those things into account so that the system is really up and running. The functionalities: automatic process management through database. We determine whether the program is benign or not, whether it updates the database to eliminate malware files, and to use it in other platforms. Android would be possible, and also Mac OS, and we're still working on Windows, and it's a very good proposal if it works, because almost all users are using or are Windows users. As conclusions, is an innovative methodology with very good results, and we're based on a feature that is common to all ransom, where the tool is being designed that complies with all pre-requirements. We have implemented it in Linux, and then we've studied the possibility of implementing it in other platforms. We've compared the results, and it has given even better results than expected. And thank you so much. If you have any